Hey friends, so we spent Monday talking about the names we give to about the 5 forces that we see, and the direction they act, how we label them, and kind of how to know what to do with them. Now, we're starting to build a model for a different way to look at motion. We're looking at why something is moving now. And we decided that that comes from a force, from an interaction between two objects. And so what we can do to make our next couple of steps easier is draw a free body diagram or a force diagram. Simply, we're taking the object, we're going to represent it very simply as a box or a dot. And then we're going to draw all of the forces that are acting on it. We're going to use arrows because remember, force is a vector. It's got a direction and it has a size. And so that arrow can represent how big of a force we're seeing act on an object. So short arrow would be a small force, long arrow for a large force. We know that we can abbreviate these using our chart. And then the last thing we do is if the forces are the same size, and some of this we're going to know based on our talk on Thursday, and we can go back and fix some of these, but if they're the same size, we're going to put a little tick mark on each of the forces that are the same to indicate they're the same. All right, so let's try some scenarios. Let's do this one together, and then when we get to the next one, I want you to read the scenario, pause it, and try it yourself, and then play again when you're ready to go. All right, so we have a refrigerator that's pushed to the right across a smooth floor, and we want to draw a free body diagram. So we're going to draw it as a square or a dot. I use a square more often than not, but if you would prefer to use a big dot, that's fine too. Now we're going to draw and label all the forces that are acting. The easiest one that I always start with is the force of gravity. We know it's going down, and I'm going to label it big F, little g. The next one, if there's a force of gravity and the object's not moving through the floor, there better be another force to cancel out the force of gravity so that the refrigerator isn't falling down, and that's the normal force. Remember, normal means perpendicular, so this force is always perpendicular to the surface or 90 degrees from the surface. And then finally, we're pushing it to the right. So our arrow starts on the dot and moves away from the dot. So if we're pushing it on the right, we're not going to draw an arrow ending at our box. We're going to draw the arrow originating at our box. And I'm going to call that a force applied. We didn't really mention that too much. Sometimes you might see it as a push or a pull. Or an applied force. Just means someone or something is doing the pushing. Okay, that's it. We need to talk about the tick marks. Which ones are the same size? Well, in this case, because we know the refrigerator isn't moving in the vertical position, it's a normal force and the force of gravity. And so 2 tick marks, 1 on each force to indicate they're the same. All right. All right, check this one out. A sled is pulled to the right with an applied force P at an angle of 30 degrees across ice. Pause it here, try one, and then press play and check yourself. Okay, you should have a free body diagram on your paper. I start with a box, and I always do the force of gravity first because it's easy. I know it's not falling through the ground or through the ice in this case, and so my normal force is supporting it upwards. And then this one's easy because it gives us the pulling force or the applied force drawn on the object already. And so I'm just drawing it at the same angle. And there we go. There's our free body diagram. Now, something to think about, and we don't know quite all of this yet, but we will get into it next week. My tick marks, I can't say that the normal force and the force of gravity are equal here because I know if I'm pulling a sled at that angle, part of that is pulling the sled upwards and part of that is pulling the sled to the right. And so I know that we're not moving in the vertical direction. And so the force of gravity has to be equal to all of the forces that are acting in the upward direction, which includes the piece in the y direction of the applied force P. I'm getting at components here. So if you are paying attention, you're thinking, oh, well, I bet trig, my sine and cosine equations could break this down into its components. And you're right. We'll talk about that next week. All right, here's the next one. Oh, you can't see it. But it says 2 boxes are released from rest. M1 is on a rough surface and M2 moves downward, which pulls M1 to the right. So this is 2 objects. So we're going to draw 2 free body diagrams. I'm going to start with M1 first. And you'll notice, and I haven't really talked about these, why is friction showing up on just this one? Well, the clue is the rough surface. All the others were ice or smooth, and so that's an indication that friction isn't acting there. We know this box is moving to the right, and so friction always opposes the relative motion, and so it better be going left. Force of gravity again, force normal perpendicular to the surface, and then it's getting pulled to the right by that rope, and so that's a force of tension. And then again, we only have the force of gravity and the force normal acting up, and so they better be equal because we're not moving vertically. And we know that tension can't be equal to the force of friction because it's moving to the right from rest, and so it's accelerating. Just like when you were pushing your object around, friction's acting on these, we just don't really notice it because it's being taken over by the tension force. Okay, box 2. Force of gravity pulling it downward, and then that rope is attached to it, and so we have a force of tension. Now we're moving from rest. Essentially that's telling us that it's accelerating, and so the force of gravity better be bigger than the force of tension. So no tick marks there, but one of the things that we'll experience hopefully soon is the forces of tension are equal. So notice I'm giving them each 2 hash marks to indicate that they're not equal to the force of gravity and the force normal, but they are equal to each other. You can do it with 3, with 4, with 5, however many you need. So this is interesting. A lot of people don't like to believe this. For whatever reason, your experience tells you otherwise. But what happens here is this is one rope. And so if I pull harder on one side, it's transferred through that whole rope, right? Like I can't have a tension that's much, much higher on part of it than the other. It has to be the same tension all the way through. And so they're equal here. This gets at a whole strategy behind tug of war, right? It has nothing to do with how hard you pull. And we're going to look at that a little bit later. But just know, you know, I could challenge a couple of you to tug of war and I could probably win because I know physics. Okay, last one. A box of mass M slides down a smooth inclined plane. Now this is a little tricky because we're at an angle. So pause it, give it your best shot, and then try again by pressing play and tricking yourself. Okay, here we go. So when I see something at an angle or on an inclined plane, I draw my free body diagram right on that inclined plane because the angle it's at is really important. So first, the force of gravity. It's going straight down. Next, force normal. It's perpendicular to the surface, so it's 90 degrees with the inclined plane. Look at those 2 forces there. They're kind of weird, right? They're acting at an angle, and our XY reference frame really isn't helpful, especially if we were going to get more forces acting on them. We're going to touch more on inclined planes later. But again, if you notice, one of them's acting at an angle, and so we can break it down into its components using trig. Okay, I believe that's it. Good luck.